Welcome to today's Oracle Machine Learning Office Hours feature highlight. Our topic today is OML4R 2.0, Embedded R Execution using R, SQL, and REST APIs, with speaker Akash Dharamshi. I'm your host, Mark Hornick, joined by Sherry LaMonica. So in this session, we continue our series on Oracle Machine Learning for R with a closer look at OML4R 2.0 on Autonomous Database, where we'll be exploring the embedded R execution capabilities through our three APIs of R, SQL, and REST. So Akash will provide an overview of the feature and then a demonstration using OML notebooks. And as always, if you have questions, please post them in the Q&A and we'll address them either during the session or at the end. And before we get started, let's hear from you regarding your level of familiarity with OML4R Embedded R Execution. Would you characterize yourself as, I've used Embedded R Execution in production solutions, or I've experimented with it for a proof of concept or run the sample notebooks? Perhaps I'm familiar with what it is, but have never really used it. Or I'm interested to find out what this feature is all about. So we have a small percentage, about 5%, that have used it in production. We've got double that have experimented with it. And then about almost half have a familiarity with it but haven't used it. And we have about 40% that are interested in finding out what this feature is. Well, this is really great. I'm glad that we're able to have you join us and learn about OML4R Embedded R Execution. And with that, let's get started. So Akash, I'm turning it over to you.
All right. Great. Thanks, Mark. Hello, and welcome to as mentioned, we will be covering embedded R execution and exploiting data parallelism for R scalability as part of the OML4R machine learning functionality. So thank you for joining us today. So let's start with the agenda for today's session. First, we'll cover an overview of OML4R and explain embedded execution. Next, we'll go into some examples and cover the APIs and functions that are associated with embedded R execution. And then lastly, we'll open up the notebook environment and walk through some demonstration of embedded R execution examples. So let's start with an overview of Oracle Machine Learning for R before we go ahead and dive into embedded R execution. So with OML4R, the Oracle database works as the high-performance compute environment to create and predict using user-created machine learning models. OML4R supports parallelized and distributed processing of machine learning algorithms and can leverage the data store or the script repository to save user-defined functions as well as R objects or models in the database. Lastly, users can invoke UDFs using SQL and the REST API and send those results to applications and dashboards via REST. So now that we've covered a little background on OML4R, let's go ahead and dive deeper into embedded R execution. So embedded R execution allows developers to store named scripts in the Oracle database, then execute those scripts in one or more spawned R engines, started data parallel, task parallel, and non-parallel execution, utilize open source packages for additional functionality in those scripts, utilize embedded R execution in the R interface, as well as the SQL interface and the REST interface, and return that data as structured data, XML, or PNG images. So what are some of the benefits of using embedded R execution? So users can eliminate data movement to and from the user's client R engine and run functions directly on database data. Users can enable data parallel and task parallel execution of user-defined R functions. Users can leverage security provided by the database when managing and saving scripts into the script repository. You can also improve the speed of transfer between Oracle database and your R internal engine while using the database to execute those scripts. By leveraging the processing power of the database server, one can achieve better scalability and performance. And by managing code from a single repository, the time to production is reduced significantly. Lastly, the user can invoke R scripts directly in SQL to return structured data, JSON objects, XML strings, or R objects and images. Here are some further use cases for embedded R execution. Using embedded R execution, one can score data at scale, such as when using the XGBoost package to build a model using a table, then score chunks of data in parallel. We can also automate building multiple types of machine learning models in parallel, for example, for different species, gender, or city, and then store the model in the database. One can build a model on those data partitions, and as mentioned, store the results in the database or access in applications or dashboards. And finally, we can also conduct simulations, invoking a function multiple times or selecting random generated data or subsets to do that. So let's explore the different interfaces for OML4R Embedded R Execution. With the Oracle Autonomous Database, OML4R can be interfaced with the R, SQL, and REST interfaces. With R, Embedded R Execution can be accessed through OML notebooks or third-party IDEs like Jupyter and Zeppelin. With SQL on the Autonomous Database, OML4R is accessed with the Oracle Machine Learning notebooks using the SQL interpreter, using SQL Developer, or another SQL client. With REST invocations on the Autonomous Database, REST commands can be done via curl or postman. And with the Oracle on-premise database, OML4R is accessed through third-party IDEs such as Jupyter or Zeppelin, or the SQL Developer and other third-party SQL clients. So let's explain when to use the R interface, the SQL interface, and REST in the context of embedded R execution and what the purposes are for each of those interfaces. With R, the R interface is for developing, testing, and the handoff of code or UDFs to IT developers for validation and logic. The SQL interface is for deploying those R UDFs in SQL-based applications and conducting scheduling via the DBMS scheduler command. And the REST interface is used to deploy R UDFs in REST-based applications. We have a link as well for some additional documentation on that as well. So now that we've covered the interfaces and some of the use cases and background, let's dive a little deeper into the specific functions that are associated with embedded R execution. In our table here to the left, we define both the R function and the corresponding SQL and REST functions and endpoints for each of the functions. So starting off with ORE doeval. ORE doeval runs the specified UDF that requires no data or accesses data within the UDF. The next function, table apply, runs the user-defined function on data loaded from an Oracle database table directly in the UDF's first argument. Next, the row apply function chunks data into sets of rows and runs the specified UDF on each of those specified chunks. Moving forward, group eval groups data by one or more column, such as, say, gender, species, or city, and runs the UDF on each of those groups. And to finish off our table with index apply runs the specified user-defined function an n number of times. So let's just represent what's happening with group apply with a quick representation. So an Oracle database proxy object is supplied to the group apply function. The data is then partitioned by category on a specific row. And as we mentioned, that can be city, species, or gender. or any other category. Each of those groups of data then has the UDF invoked on spawned R engines by the database. The results can then be stored and sent to applications or dashboards. So now that we've covered a quick representation of group apply, now let's cover some of the parallelism and the options associated with that for embedded R execution. Parallelism with embedded R execution refers to the amount of spawned R engines to manage the computational load associated to the groups of data that the UDFs are invoked on. The low service level option refers to a maximum of 2 spawned R engines, otherwise known as degrees of parallelism. A medium service level refers to a maximum of 4 degrees of parallelism, and the high service level refers to 8 degrees of parallelism or spawned R engines. When ORE.parallel is set to true, this will result in parallelism corresponding to a service level above. And parallelism is applicable to the RQ row eval and RQ group eval, and basically to the row eval and group eval functions, as was mentioned in the visual previously. So now let's cover a few examples before we go into our demonstration. Our first example will build an ML regression model on the IRIS dataset using OML4R Embedded R Execution with R. To begin, we are creating a GLM regression model and saving the model in an Oracle data store. We then connect to the database and store the UDF that was created into the script repository. We can call ore.sync to create an ore.frame proxy object. We then populate the table apply function by providing the proxy object iris, the UDF to be invoked by the name given in the script repository, and specify the function parameter DS name with the data store known as shown in the UDF, and set the database connection to true. Table apply function will run our UDF against the iris table input and create and store the regression model. We can also build an ML model on the iris dataset using OML4R Embedded R Execution from SQL. We will use RQ table eval to input an Oracle database table, which is the iris table, set the parameters being the data store name, the ORE parallel flag to true, and the ORE service level to medium. We can then set the output format to XML and input the UDF saved to the script repository. This will invoke the build GLM mod UDF using a database spawned R engine and return the resulting model in an XML format. This is an example of storing a UDF in the script repository using the R and SQL API. This example shows creating a function in R to score data. The ore.script_create function saves the score GLM mod function to the script repository with the corresponding name of score GLM mod and sets overwrite to true to update any existing instances. This next example shows how to save the same user-defined function using the SQL interface. The name of the function to be saved in the script repository is first inputted. The user-defined function is then cast as a string in the next input to be saved, and we can set overwrite to true, and this will save and update the same function into the script repository using the SQL API. In this next example, we will show parallel partition data processing using the R API. We will be using the ore.rowApply function to run our user-defined function score.glm.mod to score chunks of rows in our data set. The first input is the Oracle database proxy object. The next input is the function name, which will be score.glm.mod from the script repository. The next input specifies the number of rows in each data partition, and parallel determines how many R engines to use for this computation. And lastly, the function.value specifies the output format as a data frame. We can then save the resulting ORE frame in the data store to persist as a table. We can get the same results by invoking rq-row-eval from the SQL API. Our first input is the database table iris, and specify the parameters being the DS name, the parallel flag, and parallelism service levels. The next input is the output format being a JSON string. The row_num specifies the number of rows to be processed in each invocation, such as the same way we did in the R interface. And this is now set to 10. And lastly, we will input the function to be invoked on each chunk of rows, which is saved in the script repository, and that is inputted as score.glm.mod. This will score the data 10 rows at a time, utilizing 4 spawned R engines specified by the medium service level, and invoke score.glm.mod on each of those chunks of rows. So now let's move into the Oracle Machine Learning Notebook environment to look at more code examples of embedded R execution. This is the Oracle Machine Learning Notebooks environment. We will be demonstrating embedded R execution and walking through some examples explaining this. So first, we're going to go ahead and import our necessary libraries. This will be the ORE and Lattice package. Next, we will go ahead and create a proxy object for the iris_r table, and we'll do that by calling ore.sync. This will create a proxy object for us. So let's go ahead and build and score a linear model directly in R first, and then move into the embedded R execution. So to begin, we will be pulling the proxy object that we just created and bring it into our local environment. Next, we will go ahead and create a linear model predicting petal length with petal width using that data table. We can just run some predictions on this and input the model that was created and in the data table to get these predictions. We can assess some of the model quality, calling summary on our model, and get some of the details there as well. And now we can run some visualizations and output some of the details of our model and the fit. So now let's move into building the same model using embedded R execution. So to begin, we'll be creating a function build lm1. This function will create a model and also output some of those fit details as well. If we just call that function, we can see that it is outputting our model, and it's also outputting the visual the way that we want it to be. So now, if we want to invoke this function using embedded R execution, we can run the table apply function, as mentioned in the presentation. The first input is the data frame proxy object. The second input is the parameter ds name, which was a parameter of our UDF. And the last input will be the UDF itself. By running this, we can see that it gives us the same details as just invoking the function. So we can verify that this is unified. Further, we can now save the script that we just created into the script repository using ore.script_create. And by running ore.script_list, we can actually see that this function is indeed in the script repository. So this now, we will be running the ore.tableApply function one more time with the data frame proxy object, the same DS name, but just notice that the function name is now in quotes to represent that we are invoking the function in the script repository. And as expected, we do have the same outputs there as well. So now we can move into representing the ore.rowApply, which chunks our data and runs the UDF on each chunk of data. Let's create a function score lm1, which will score data using the model that we just created and saved. We can go ahead and create this function, which will load the model in our representative data store, run the predict function using that model, and then output some of the details. We can then run script create one more time, pass in the scoreLM function, give it a name, and overwrite any existing entries. We can now run ore.rowApply using our data frame proxy object, passing in the function that we just created, representing a data store, and specifying the number of rows to chunk our data and how many engines to use for this computation. And by running that, we are able to start to see that we are scoring our data accordingly. So let's now represent how we can build one model per species using the group apply function. Let's create the UDF build lm2, which will create a model similar to build lm1. We can save that model into the script repository and then run group apply with that function. Pass in the data frame proxy object, and now we'll specify our index, which is the column that we want to pull out the categories from. And because we pass in the species column, we will be creating a model for each of the categories within that column. We'll specify a data store name. We'll specify the function that we want to pass into group apply and the amount of engines to process this computation. And by running this function and by running group apply, we get a representation that there is a linear model that's being built for each species. And this represents how we can use group apply to create multiple models for different categories within a column. We can then quickly view some of the data store components and notice that the data stores that were being utilized have content and the models saved within them. So we can actually verify that the data store is active, and we can verify the objects within the data store as well. And now, if we can go ahead and run table apply one more time using the iris data frame proxy object. We can pass in the function build lm1 from the script repository and specify a data store name and save the model that's being created from build lm1 on this proxy object to mod. This will store our model, our outputting model. When we utilize mod in regular predict functions, we can see that we can go ahead and get predictions using the model that was created from the table apply function. And we can also assess that model quality directly from the table apply function. And we can assess that model quality using summary. This gives us those details here. So moving back to the group apply function, the group apply function can be used for simple as well as complex computations. And here, it's simply used to count the number of species in each set. So we create a function named group count, and we get the number of species for each species that exists in the data frame in the proxy object, or any of the data sets that are passed in. By running the group apply function with the proxy object, the specified index, passing in our function, we can actually see that it will get the number of species for each species here. And we can see that that's outputted accordingly. And as mentioned, the index apply function allows for the same function to be invoked a specified number of times. So in this UDF here, we are going to be computing the mean on a randomized set of numbers and then returning that mean. So that UDF is labeled compute mean, and we pass that into our index apply function. And we specify the number of times that we want to run this function. And here, if we specify the number 12, we will see that this function will be invoked 12 times, giving us the ability to create simulations on a greater scale. So now we've covered the R interface. Let's look at how we can use the SQL interface for embedded R execution as well. So, albeit there are some steps that are needed in order to give the relevant user access, and some of those steps are included here, but basically the admin user will need to create a user on the access control list, confirm that user is on the access control list, and then obtain an authorization token. And we'll walk through that here as well. So to obtain an authorization token, we have a function here, which basically simplifies that. And that's outputted here. We can pass in some of our details into this function, and that will create the authorization token. As mentioned, we will need to add the user to the access control list. And to do that, we will need to run the rq append host ace function in the SQL developer as an admin. So that step has been taken care of on the back end. And once again, when we run this function, this will set the auth token. And that's been done on the back end as well. So let's go into the embedded R execution from the SQL API, and let's actually run some of the functions that we created earlier. So to begin, the RQ table eval is the table eval function in the SQL API. And what this will do is input a data table directly from the Oracle database. And in this case, that's the iris_r. We'll specify our parameters, being the data store name, the parallel flag, set that to true, and the service level. We'll specify our output format to an XML and pass in the function that creates the model from our script repository. And in this case, we'll be passing in build lm1, which will create that model. And here, by running that, we can actually see that the output format is an XML string, and it is giving us the model corresponding to this table and function. Next, we can run the RQ row eval, which is the row eval function, and pass in an Oracle database table as well. Specify the data store name, the parallel flag, set that to true, and the service level set to medium. We'll specify our output format to be a table. And as mentioned with the row eval, we'll be setting the row numbers to be chunked with. And in this case, we'll be setting 50 rows per chunk, and we'll be scoring 50 rows per chunk using the score lm function that's also stored in our script repository. And by invoking that function, we can see that we are starting to get some predictions on our data. And this is supposed to predict petal length. And we can see that output here as specified with the output format. To continue, we can represent the RQ group eval, which is the group eval function, pass in the database table, set the parallel flag to true and the service level to medium, set the output format to be a relational table with species and model type. And basically, we want to create a model for each of the categories in our species. So in the R interface, that is considered an index, and that is also the same concept here is which column do we want to take our categories from? And we specify the species column, and we pass in our build lm2 function, which will create a model for each of the species categories. We can see that this is outputted as a relational table representing the species and model type. So now that we've gone through and covered some of the SQL API, that kind of gives us a representation to look between how the R interface and the SQL interface have some similarities, but also some differences. And to wrap up this notebook, we can represent some of the functionality to return images directly from embedded R execution. So we will create another user-defined function here, which will be the random red dots. And this will just create two plots that have randomized numbers of red dots on them. And so we go ahead and create our user-defined function here. And we can just save that user-defined function in the script repository. We can go ahead and just invoke our function directly from R just to make sure it works. And we can see that we get plots as necessary. We can then invoke the same function that we just created, which was random red dots, and do that using ore.doeval. So this ore.doeval, just as a reminder, runs the function without any table inputs. And so we run ore.doeval, and we can see that we get the same output as before. And if we wanted to invoke this function from the REST API, this is how we'd do that. And we'd set the graphics flag to true. We'd input our function and then have this curl post command here. This is just one more way to create our random red dots 2 function, basically by altering the way that our plots are set up. And we can go ahead and do the same thing here, where we create our user-defined function and save that into the script repository. And again, if we run our doeval function on our random red dots 2, we will get the outputted image plots as we want there. And now that takes us to the end of our demonstration of walking through embedded R execution from the R interface as well as from the SQL interface. So to wrap up, here are some relevant links to learn more about the Oracle Machine Learning Platform. You can view our homepage. You can view our blogs for a range of helpful and educational topics, and as well as our GitHub to view currently available notebooks and examples. And we also encourage you to subscribe to our monthly office hour session and review our full suite of documentation. And with that, I would like to thank you for your time. And please feel free to send any additional questions about embedded R execution to my email at akash.durumshi@oracle.com, as well as send any further questions to Sherry LaMonica or Mark Hornick. Thank you for your time and have a great day.
Okay. Are there any additional questions that anyone has? I think one of the things that came up was, can we specify more than one column to partition data when we're doing, say, a group apply? And the answer to that is yes, you can specify more than one column for that, and we'll partition using that as essentially the key and feed the data to each of the R engines that are there. All right, I think that brings us to a close. Thank our speaker again, Akash, and until next time, have a great week. Take care.